In this tutorial, I will discuss the paper Theorems for Free by Philip Wadler. This is a very well-known paper, and this is an appendix to my tutorial series about relational parametricity. The goal of this tutorial is to explain the relationship between this paper and what is explained in my tutorial. When I first read the paper Theorems for Free, I could not understand why these theorems hold. I could not understand how to write those theorems. And I could not follow the reasoning in detail. So I will show you what is different in this paper from what I explained in my tutorial and why it was not easy to understand. So this paper says, from the type of a polymorphic function, we can derive a theorem that is satisfied. Every function of the same type satisfies the same theorem. This is a very concise formulation, but it's entirely correct and clear. And then we are asking the question, so first of all, given the type of a polymorphic function, how do we write that theorem that it's satisfied? As a practical programmer, I may not need to go through the proof of why this is true, that it satisfies the theorem, but I need to know what it is that it satisfies. So in a different part of the paper, he gives examples of free theorems. These are the examples for different functions. In his notation, x star is the same as list of x. So it's a list of elements of type x. And a star is the same as f map of a. So f map for the list functor. So that's fine. So I can understand that. But how do I come up with these theorems or equations? So filter satisfies this. How does it follow from the type of the filters? Because by what is said here, it follows from the type what theorem it satisfies. The paper does not actually explain very clearly how to do that. It gives some examples, but it does not explain how those examples work in detail. And then the second question is, why is that true? So how do we prove that every function actually satisfies of that theorem? Well, in fact, there is an assumption here that the code of the function must be fully parametric, or where they say it comes from polymorphic lambda calculus. But this is not very clear from the paper either. So what are the restrictions on code that are necessary for the function to satisfy the theorem? Because clearly, without any restrictions, that's not going to be true. So that, unfortunately, is not explained very well in this paper. So I'll show what's happening in this paper. Is that the first thing he says is that the key is to read types as relations. So now that is not obvious, how to read types as relations. Relations between what types are going to be. So if you read what follows here, there's a relation between a and a prime, okay? And then he gives you an example of a graph relation from a function a. Well, that's clear. But how do you read types as relations? So we need a relational equivalent for the type constructions. So, but he doesn't explain very clearly. It's going to be a relation between what types? Because then he says, for any relations, the other relation is defined. Well, let's find, how do I translate this into a relation? Like, for example, I have a type such as a times a function a to b. So how do I translate that into relation? First of all, what are going to be the types between which this relation is going to be? So this is a type. I'm going to translate that somehow into a relation. But a relation between which types? Not between A and B, obviously. So actually, it needs to be that we have two more types, A prime and B prime. And then there will be a relation between this type and A prime times A prime going to B prime. So for each type parameter in the initial type expression, I need to introduce a pair of types which are going to be related. And then I need to introduce a relation between A and A prime. I need to introduce another relation between B and B prime. And then, only then, I can talk about what relation this is. Now, this detail, at first you need to do this. You need to introduce new relations for each free type parameter. This is not written here in the paper. So I explained that in my tutorial, that actually you have to think about this as a type constructor, f of a, b. And then you need to lift two relations to this type constructor with respect to the two type parameters. And that's the construction that I explain. And he does not explain that in the paper, but that is actually what is necessary in order to follow what is happening here. Pairs are related if their corresponding components are related, but he didn't explain where these A and A prime came from. And so that's the crucial missing information that the reader cannot really guess, that you have to introduce arbitrary new relations between A and A prime, B and B prime, and only then you can lift them to a relation between f of AB and f of A prime, B prime. So that is implicit in this description that's not explained. And so unless you already know this somehow, that you have to do this, you won't be able to guess. Then you go on, then you read. All right, so then you have functions. For functions, it's a similar story. And then comes here the construction with the universal quantifier. So how do you translate a relation, a type with a universal quantifier into a relation, right? So what we're doing here is we're translating types into relations. So we have type expressions like these, and we need to translate them into relations. That's what is supposed to be done here, to read types as relations. So how do we read this type as relation? So we have, let's say, for all A, we have some type constructor f of A. So this is a type. Well, the type constructor f could have also other type parameters. Let's not write them now. But this is a type. Let's call this type T. So how do we read this type as a relation? So first question, relation between what types is this going to be? And second question, how do we define that relation? So we are supposed to define that relation. Let's say f, let's say, for example, f of A equals something like A going to B times A. Doesn't matter. B could be another type parameter, fixed type, doesn't matter. So let's say we have some type expression like this. How do we translate that into a relation? And a relation between what types is it going to be? And if you read what is written here, we have to interpret the universal quantifier as an operation on relations. No, that's not true. We have to translate the type expression such as for all a f of a, we have to translate that into a relation. We don't have to interpret the universal quantifier as an operation on relations. So that's confusing. This next sentence is even more confusing. Let cursive f of cursive x be a relation depending on x. So that is completely confusing. Why do we suddenly talk about a relation depending on x? So obviously another relation, because the cursive letters like these, they denote relations. All right. So, but what is this new function cursive f? The function from relations to relation. No, it doesn't correspond to. You just defined it like that. So what is that? Where does it come from? How do you get from here, where you had a specific type expression like this? How do you get from here to a function from relation to relation? And then such that for every relation A, there is a corresponding relation f of a between f of a and f prime of f a prime. Immediately another question, what is f prime? Where does that come from? It is not explained. We were supposed to explain how to translate a type expression like this into a relation between some other types, but we haven't explained that. Instead, we introduced some f prime. We introduced some cursive f without defining where that comes from. We don't know what f prime is and where that comes from. And suddenly we're talking about a relation between these things, f prime and so on. And we define something, which I don't know why we define that and what does give us. Polymorphic functions are related if they take related types into related results. Okay, well, I don't understand what we have defined here, and I don't understand why we have defined it. We have not answered this question, how to translate this into a relation. Interrelation between what? We haven't explained. So, and then you read, using the definitions above, any closed type T containing no free variables can be read as a relation T to T. Okay. What about types that are not closed, like this type that has another type parameter that is free? How do you translate that into a relation? Not clear. And actually, when you read such a thing, you don't understand this. You think, okay, well, this is just a detail. I kind of understood the other parts, so let me skip this. But actually, no, you can't skip that, because without the construction with the universal quantifier, all you will have from these relations is an identity relation, because constant types, he says, are read as identity relations. So translating that into equation, I would say if you have a constant type int, then the corresponding relation is an identity between int and int. Then I can take products and I can take functions from, say, int. I can have a product of int, right? So that's, let me write it in notation that he is using, which is a more mathematical notation, the product. So that goes into the product of identity relations, which I would denote like this, just so that it's kind of more clear that this is not a type. This is a product of two relations. And that actually is, again, an identity relation of type int to int. Okay, then you have a function, let's say int to int, and that function type is translated into an identity going into identity, and I have this notation in my book. For this paper, I don't think he uses that notation. He uses just an arrow here, the relation. So I just put a box around that to be a little more clear, but that doesn't matter. Again, that is going to be an identity relation between functions int and functions int, because if you translate the definition of the function construction here, functions are related when for all related arguments, the results are related. And if this is identity and this is identity, and so far we cannot construct anything than identity relations, then this is going to be for all identical x, the results are identical. So that means the function f and f prime are the same function. And so we can only get an identity relation from these constructions. The list mapping here, again, will just give you an identity relation. So if you say list int, it will just give you an identity relation between list int and list int. And so when I first read this paper, I skipped this part because I could not understand what is going on. Why are we suddenly talking about some new cursive f and f prime that weren't promised to be talked about? So I just skipped that. And then I said, okay, well, we only get identity relations. So this must be an identity relation. But that is not true. And also this is kind of trivial. This is not a useful theorem that any term t, any code, in other words, any expression t is in an identity relation with itself. Well, that's trivial. It's always true. Don't have to prove that. So obviously, this is not what this theorem says. So this relation, cursive t, is not identity. But what is it? So in my tutorial, I explained that this universal quantifier is actually important because unless you have type parameters that are universally quantified or some maybe outside, but you have to have them universally quantified, the parametricity theorem doesn't give any interesting results. And that's exactly what is happening. If you don't have type parameters, if all your types are specific fixed types like integer and so on, then you will only get identity relations. And that's not going to be any kind of interesting information. And so in my tutorial, I explained that what you need to do is you need to take an arbitrary relation R between types A and A prime, where A and A prime are arbitrary types. And then you need to lift this relation to the type constructor F. And so for values T1 of type, let's say T1 of A, of type F of A, and value T2 of A prime of type F of A prime, the values T1 of A, T2 of A prime must be in the relation, which is the relation R lifted to F, which I denote by R map F of R in my tutorial. So that actually is the condition for lifting to a type constructor with a universal quantifier. So this is actually the condition for the values T1 and T2. So if T1 and T2 are values of type T, it means these are functions with type parameters, usually. It means that we can take T1 of some arbitrary type and we get F of that type. But notice it is a relation between F of A and F of A prime. There is no F prime anywhere. It cannot be. There cannot be any F prime because we are translating a type into a relation. we need to formulate what is the relation between T1 and T2. There is not going to be any F prime anywhere on the horizon. So when you read this, you are completely thrown off, confused, and you don't understand what's going on. When a student reads this, so let me rant a little bit. When a student reads this, the student thinks, I'm stupid. I understood previous lines a little bit, but now I understand nothing. I need to read this again. So the student goes back and reads this again, but this is not going to illuminate, because actually there isn't an explanation in this paper about this particular detail. And so no matter how many times you read that, you won't get it. Unless you read something else that doesn't introduce the same things and doesn't talk about reading types as relations in this way. Reading types as relations is also not an adequate starting point, because what you need is to lift relations to type constructors. You don't just read types as relations. So, for example, this type can be read in different ways as a relation, depending on whether this B is a fixed type or this B is a type parameter quantified outside, for which we have some arbitrary relation between, say, B and B prime. And then if B is a fixed type, then you would have a relation between f of a. So when we want to lift with respect to the type parameter a only, and not with respect to type parameter b, because it's fixed. So we will have a relation between f of a and f of a prime, which means you will have a relation between a to be a and a prime to be a prime. But if b is quantified somewhere outside, then you would actually want to write a relation like this. You would write to say FAB, actually, introduce a different type parameter, B prime, and then you would have this kind of relation, which is going to be different. And so you would have a relation R here between A and A prime, and from that R you would lift to a relation like this. And here you would have a relation R between A and A prime, and a relation S between B and B prime, and you would lift both of them at the same time to this type constructor to get a relation between A to be A and A prime to B prime, A prime. So this is what I call the simultaneous lifting. I call this R map 2 of R and S. And here, so this is going to be a relation of this kind, of this type. And here you would have just an R map F of R, which is going to be a relation of this type with B fixed. So, and then you say, oh, but what if I just take an identity relation instead of S and B is equal to B prime? Well, it's supposed to be the same thing. Yes, so then you have to prove that the lifting procedure actually is the same. Sorry, let me make it clear. This R map is actually the same as R map 2 of R and identity. Identity of type B to B. So you have to prove that lifting of two relations at the same time has this property, that if you fix one of the type parameters, it's the same as lifting an identity relation. So you can prove that. It's not difficult, but this is a detail that you have to go through. So there is a difference between lifting just one relation with respect to just one type parameter and lifting two relations with respect to two type parameters. This needs to be spelled out. This is not spelled out in this paper. So then when you go through examples here, like for example, this fold, then you just say parametricity implies that. But because you did not really understand what that was doing here, what is this F prime here, what is this calligraphic F doing here, cursive F, you don't understand how to go from here to here. You just memorize. You memorize that this is what you do. Well, actually, this is, I believe, a typo. This must be a calligraphic Y here. Well, doesn't matter. So when people go through this paper many, many times, they memorize the examples. They don't really understand what is being done at a high level. They just memorize the examples. So they go through the examples, they can reproduce these derivations. But then if you have a different example, you're never sure what to do. And that is a problem. So another thing that this paper does not explain is that sometimes the theorems are just simple equations. So let me show examples here. Sometimes they're just simple equations, but in other places, they're not simple equations, they're more complicated. So for like here, if for all x something holds, then this holds. So it's not just a simple single equation for the function sort, but this just a simple equation for the function concat. And so the difference is that the type signature here is that of a natural transformation. It is the type signature of the sort f of x going to g of x, where f and g are both covariant or both contravariant. And then this is a type signature of a natural transformation, and that has a naturality law that you can write once and for all functions f. So f lifted to f map f of f. So that is going to be from f of x to f of y, say, preceded by some function t is equal to function t after f map g of f. So this is a general naturality law for any two type constructors f and g, and then here you just have specific examples of this type constructor, like a list of x or something like that. Here it's simpler, the type constructors. So you have to go through that, and then you see these are okay, but these are all just naturality laws. But these are not naturality laws, and that is because these type signatures are not signatures of natural transformations with respect to the type parameter y here, for instance. So that's the problem, that it's actually not easy to formulate this property. And there are actually some questions about formulating these properties that the paper does not go over. Well, this was the first paper that explained this technique. But in order to be proficient in using this technique, you need to understand that actually, first you need to derive a relational law, and then you sometimes can simplify that by using function graph relation, but sometimes you cannot simplify it. So in my tutorial, I showed a curious example where I was considering a type of this sort for all a to r to a to a. Now this type is actually equivalent to r. But this is not at all simple to prove this equivalence. And in my tutorial, I made it a little easier because I did not just take an arbitrary type r. Here, I took 1 plus r. Or in the Scala syntax, this was option of something. I think in my tutorial, this was denoted by k. So in Scala, this is option of k. So when you prove that this equivalence holds, you need to use the assumption that this function is implemented in fully parametric code. So then you can use the parametricity theorem and derive the parametricity naturality law, relational naturality law for this function. Now, if you go through the techniques of this paper, you will not be able to prove this statement, because actually this type signature is a type signature of a natural transformation, because this is covariant in A. So this, we can denote this as f of A, and that is covariant in A. And so the type signature is f of A to A, and that's a type signature of a natural transformation. So if you go through this technique of deriving the free theorem, you will just derive a naturality law for this function. But this naturality law is not strong enough to prove the properties of this function. This function has a complicated type signature, and that I showed that in the last lecture of my tutorial. That naturality law is not sufficient. You have to go through the full relational naturality law and use a relation that is not a function graph, and some non-trivial relation that is not obvious how to choose, and only then you are able to prove the type equivalence. And so this, you will not get it from this paper, because this paper only shows you how to derive certain things from examples, and then you will just derive the naturality law if you follow all these examples. Another thing that this paper was supposed to show is a proof that these laws actually hold. But if you look at the proof, you won't understand how it is done. There's a very complicated theory being developed here with frames, some kind of U sets, and so on. Complicated notation that programmers are not very familiar with. It's not explained very well, because this is something that computer scientists know, but practicing programmers do not. Programming language theory. And then you see, for all x, blah, 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 you don't really understand what this is, and the proof is a joke. You don't, it's straightforward, it's just a straightforward. Well, actually, in my tutorial, I go through this proof. It is straightforward, except that you have to prove a number of technical properties, which I do sometimes prove, or sometimes I just indicate what they are for lack of time. But for instance, you need to prove the property that I talked about, where you lift an identity function, you lift an identity relation together with another relation, and the result is the same as if you were lifting just with respect to one type parameter. So this is a technical result, and it is not difficult to prove. You have to go through the cases. Another thing that this paper doesn't do is co-products. It does products, but does not do co-products, A plus B. Now, you could actually say that this is okay. You can encode co-products using universal quantifier, because it's the same as for all C, A times B, A plus B to C, and then, so that is just unit lemma, but this is the same as A plus B, and then you say that the function A plus B to C is equivalent to A to C times B to C. So then you have here no more need to do co-products. Products are sufficient. So you can encode co-products via products, but it is inconvenient to go through this extra step when you have products and co-products in your actual type signature. It is more convenient to have a direct recipe about how to lift relations to co-products. So this is another omission in this paper. And then finally, the proof is just going through each of the inductive cases, but then you have to prove several technical results about this lifting of relations to type constructors. It is not enough just to talk about relations between T and T. So type T, according to this paper, is translated into a relation between T and T. Now that is not enough, because type T could have universal quantifiers inside, and then you are forced to talk about relations of this kind or of this kind, and then you have to make distinctions between them. And this paper does not give you the tools to reason about that. And so the proof is actually, yes, it is straightforward, but it requires some technical results that are not explained. So to conclude, this paper has a number of disadvantages if you are using it to learn for the first time what is the relational parametricity and how to get these theorems for free and how to use in practice this theory. Unfortunately, there are no other tutorials other than my tutorial that explains these things step by step. There have been a tutorial that is called here parametricity tutorial here. So let me show it where that is. It's this one. So there is a tutorial in 3 parts using the Haskell notation and then this notation with cursive R. So the cursive R is this operation that takes a type and gives you a relation. This tutorial also doesn't explain very clearly between what types that relation is going to be. I believe because it's just trying to understand Wadler's paper, and Wadler's paper does not make it clear at all. So later in this tutorial, there are further confusing things that because types and relations are denoted by the same letters. And then if you go through examples, you will have to do certain things that are not explained in the previous text. Like for example, we have mapping a free variable A to a relation A from A to A. Now it's not explained that you have to introduce new arbitrary relations and new arbitrary types, and you have to lift that relation to a type constructor with respect to those type parameters, blah, 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 blah. It's not explained in this tutorial. Instead, it goes through examples. So I believe this author also went through all the examples in Wadler's paper and just memorized what you have to do step by step, instead of understanding at a higher level and following a guiding principle. So in my tutorial, I believe I found a good guiding principle, which is to lift relations to type constructors. So that's the major difference between my tutorial and all other material on relational parametricity. In my tutorial, a central place is occupied by this construction where you have a relation R between, say, A and B, and you have a type constructor F depending on a type parameter A, and then maybe some other type parameters. And I lift the relation R with respect to the type parameter A I obtain a relation like this, where all other type parameters are fixed. So from this, I have a clear procedure how to build that new relation, which I denoted in my tutorial R map of R. And I can do this with one relation with respect to one type parameter, or if necessary, and sometimes it is necessary in the inductive cases, I need to lift several relations at once with respect to several of the type parameters. And yet there are still other type parameters that are held fixed. So this is the construction that occupies a central place in my tutorial. This construction is clear. I don't talk about reading types as relations or characterizing anything, or I don't do that. I don't also need to use any kind of special notation, although it might help to have notation that makes things quicker to write, but I don't do that on purpose in my tutorial. I just use Scala code-like notation. For example, this is like a Scala code where you apply a function to the value. Whereas in his notation, that's going to be some here in this tutorial is going to be much more difficult to understand. What are you transforming? Which type parameters are held fixed and which are not, and so on. So that is the main difference between my tutorial on relational parametricity and pretty much all other existing tutorials that all begin with this paper, Theorems for Free, and all try to understand and interpret it. I gave up interpreting this paper and understanding it, and instead I found my own way using this construction of lifting relations to type constructors. Certainly there are limitations in that approach, and I'm not sure how you can do, for instance, the same approach with type constructors, where you have, say, for all type constructor F, which I would in Scala write like this, and then I have, well, let's say f of A to f of B, whatever. How do you reason about this kind of parametricity applied to type constructors? But I'm sure that this can be figured out in a similar way. It is important to have a clear guiding principle and standpoint where you understand every detail and you understand why you're doing it and what direction you're going through. And so I believe my tutorial fills an important void in this sense. It explains, at least in some way, step by step, what parametricity is, how you prove that it holds, and how to derive without having to prove that it holds. Suppose you believe that it's correct, don't have to go through the proof, but how do you derive the statement of the theorem that your function satisfies? Is it a naturality law? How do you recognize that it is a naturality law? How do you write it down? How do you recognize that it is not a naturality law, or that you are not in the naturality law does not give you enough information? You need a more powerful law. So all those techniques I explain in my tutorial.